for the introduction, and thank you very much for the invitation to be here. It's an honor, it's a pleasure to see such a young audience and to have the chance to talk here. Actually, I want to say on a personal note, even though she only knew about me since she was in middle school, she got involved with the Laplacian Foundation when she was 7 years old, and so I've known from Liz for a long time. That shows how old I am also. Okay, so what do I want to do today? I want to talk to you a little bit about, Liz mentioned my research lies at the interface of geometric measure theory, harmonic analysis, potential theory, and PDEs. And what I want to do is we're going to start by talking first about rough and smooth, and then we will talk about the different mathematical lenses. And what I want to do is to hopefully illustrate some of the ideas on the sort of things that we can do in the area that I work with, okay? But because rough and smooth are very broad terms, and I'm sure something comes to mind to you when I say rough, and something comes to mind as smooth. First thing I'm going to do is I'm going to show some pictures of rough, what I think is rough for this talk, some of the pictures of smooth, and then we'll go from there, okay? So, my first picture of rough, what are you seeing? Actually, you're seeing the fossil of a fern from Colombia. What do I want you to look at? I want you to look at the little leaves, how they come together. Okay? Another example, this is a Mandelbrot set. So the math department has a picture. What is this? This is the fractal, or the thing that was on your t-shirts when you were little. Okay, depends. But we will talk about that. One of the things I would like you to do, I think in math, lots of it is patterns. Start looking to see if you see patterns. What is this? This is a romanesco. What is a vegetable? I think my name, my mother was a cauliflower, father was a broccoli, or the other way around. I'm not exactly sure, but that's what it looks like. So we'll see bigger pictures of that. And this is a Radiolaria. What is a Radiolaria? It's something I will explain in a little bit, and I won't say much more. Just when you look at the picture, we'll talk about them. They have a meaning here. Okay. So these are the sort of things that I think when I'm thinking of rough. Okay. Now let's go to smooth, and you see there's a question mark. We'll see why. So, what are you seeing there? You're seeing a subfilm, okay? The subfilm, nice features, has boundary, that has 3 pieces of the boundary, has some force. You see it? Oh, we think they're very, what could be smoother than the subfilm? Oh, but, and then here you're seeing more soap. Let me see if and you're seeing tomatoes. So the tomatoes, we think of them as very smooth, but there's these creases, correct? How smooth is that? And let me see, I want you to focus, it's difficult. So you see the bubbles, here you see some things, that's why maybe the question mark. I would like you to look at these, but I also would like you to keep in mind these little pieces here for the future. Okay? But so, when I talk about rough, I'm thinking of things whose boundaries look like the first picture. When I'm thinking of smooth, I have this sort of thing in mind. Okay? One thing I didn't say, I love questions. Feel free to ask. Okay? And I love introductions because this is how I can hear myself talk. Okay. So these are my rough objects, and my smooth objects. Okay. So what are the lenses? I would like you to think of math in this context as a microscope. And I have different lenses that I'm going to put on there to try to distinguish between these objects that we saw at the beginning. And so the lenses I use, the first one is called geometric measure theory, GMT. And what's going to happen in this talk is you're going to have this 3-slide introduction to GMT. Then you will have a 3-slide introduction to harmonic analysis. You can imagine each one of these introductions are going to be very biased. They're going to be introductions that I need. Somebody else given this talk could introduce this subject and talk about things that have nothing to do with what I'm going to talk about. And then I'm going to talk a little bit about partial differential equations. So what the goal is, I'm going to do an introduction to each one of these areas. I will show you then how to put them together to try to distinguish between these objects. Why did I choose the analogy of a microscope and of lenses? My parents were both pathologists. I saw lots of microscope and then looking through lenses. Maybe that's what so I know that if you color your example differently, you see different things. Hopefully that's what I'll manage to convey. Okay? Okay, so your introduction to geometric measuring theory. So the plateau problem asks whether a minimal surface with a given boundary exists. What on earth am I talking about? You make a boundary out of a wire, you put it in soap, and this is something that comes out. Okay? And so this film is basically, it will be your minimal surface. Again, remember patterns. There's everything. This is like a game of patterns. Remember the first pictures we saw, and look at this picture. Okay? Look at how the soap, the very smooth pieces come together. This question was raised, this existence question was raised by Lagrange in 1760, but is named after a physicist, Plateau, who experimented with soap films. And so what I like is, sorry, not all the pictures fit in the same slide. So here are, well, we'll have the chance to see these two pictures together so that we can try to see the similarities. So it looks like these are so.
Can I ask a question? Is there a boundary here?
In these ones, there's no boundary. So, sometimes we look with a boundary, sometimes not. But we always look for the purpose of this question to look inside that boundary. Okay, let's look at the two pictures together. So, I want you to take a minute and try to see if you see similarities. Let's see how the soap comes in together. You have three beautiful bubbles, layers, and then there's these things here. Okay? And look, they're not too far apart from these. There's a sheet of soap here, there's one here, and there's another one on the back. These, of course, they're more complicated things that are going on here, but there's some similarities here. Okay? In fact, you've seen all the possible options in which soap can come together. Okay. So, the plateau problem lies in an area that's called calculus of variations. And the geometric measure theory is the tool used to show existence. Because I can ask this question, does there a surface exist such that blah, 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 but how do I show that such a thing exists? So geometric measure theory gives you the context to show something like that, okay? And in the three-dimensional Euclidean space, Douglas and Rado solved this problem in 1930, and in fact, Douglas got the first Fields Medal for the work in 1936. So this, why do I say that? This was very important, and still is a very important question. Many things have happened, we can say many things, but we still have lots of questions. And in Rn, so remember, that was in R3. In Rn, when n is greater than 4, Reifenberg in 1960 gave the first proof of regularity of minimizers near flat points. Okay, so let's go back to that kind of cube, and when you saw they're very flat, very beautiful pieces, and there's some pieces that are not flat. Okay? And so even showing that the flat pieces were really, really nice took lots of work. And you see there's a difference between 1960 and 1936. Lots of mathematics needed to be developed to make sense of the fact that you are the boundary of somebody.
Are there any flat points in the bubble example?
Yes, thank you. Let's go back to the bubble here. So what's a flat point? A flat point is relative, okay? And so let's look at the bubble. When I say flat, it's infinitesimally flat or flat at the right scale. So imagine, take this point here, okay? Take a plane, a tangent, you see a well-approximated plane, a tangent plane, and you say it's very close to the plane. It doesn't mean that it has to be flat. It means it has to be close to flat. Okay? Contained in a little rectangle or very small.
Is that closeness defined like how in order of vanishing?
Initially, to start with Reifenberg show, it didn't even need to be vanishing. It's the distance between two sets, and in this case, let's say the bubble and the plane is defined in terms of the Hausdorff distance, which tells you you're measuring how, if I draw a neighborhood of the plane, okay, the neighborhood of the plane, how close is my bubble? Can I fit my bubble in there? And if I draw a picture, a neighborhood, let me draw it. And if I draw a neighborhood of the bubble, can I put the plane in there? Okay, so let's imagine. This is the bubble. This is the plane. And it's flat in the sense that there's a small number here. This is R. This is epsilon R, where I can put it. I don't think that's going to be very, very small. I need it to be small enough. That's what Reifenberg needed. There's lots of different versions of it. And the same thing happens. And now if I draw you see, the plane is contained with us. Does that make sense? Did I answer your question, or?
Yes, but what did you say about vanishing? Is it or not defined about vanishing?
Okay, so what Reifenberg showed is that if you're a minimal surface and you're flat with a small enough epsilon, because you're a minimal surfaces, then that epsilon goes to zero as the radius becomes smaller and smaller. But that's a consequence of being a minimal surface. Okay? So maybe I'm going to given your question, I'm going to actually make a parenthesis and give you an idea of how things go. So calculus of variation asks, does there exist a minimal surface, an energy minimizing so a minimal surface with a given boundary? Geometric measure theory puts it in a framework that allows you to say, yes, the thing exists, but a priori, it can look really horrible, okay? Reifenberg showed that even though it could be horrible, at the nice points, these smooth like that, it had that property with some epsilon, small enough, but not that. Then you put these back into the machinery. Okay, it's a minimal surface. Behind the minimal, there's always an equation. Okay? And I have to say, my lawyer disclaimer, there's an expert in the room. So if I were not to be telling the whole truth and nothing but the truth, he's going to excuse me for the time being. So, and he will not complain until the end, okay? So now we know that we're flying enough. And I can say where I'm lying, but I'm not going to go there. So it's complicated to give a talk. But it's flat enough. Then you put it back in the machine, and the thing tells you actually it's getting flatter and flatter and flatter. So that epsilon that I drew there is an epsilon of R, and it goes to zero. And with more information that Reifenberg also produced, you can show that it actually is going to zero like the power. But we're not there, and that's not the problem. But that's where the flatness is. Okay? So the vanishing is a byproduct of being a minimizer. But we can use this concept even if we don't know. Okay. And so that's where we were, and the flat one. Okay. Now, let's go back to the Radiolarias. How did I learn about the Radiolarias, or what are the Radiolarias? The Radiolarias are microorganisms that live in the bottom of the ocean and that move or propel themselves by taking water and letting water out. Okay? I learned about radiolarias not in my biology class, but in a paper of Jean Taylor, who was studying the singularities for minimal surfaces in R3, and basically they all correspond to the shape of the radiolaria. What on earth am I talking about? I want you to look. You see, remember the soap? When there were lots of bubbles? Look, doesn't it look similar? And here, remember when I asked you to look at that triangle? Doesn't it seem like there's similar things here? Well, it's not a coincidence. That's exactly what it is. Radiolarias have become very popular. And so what you're seeing here is really the skeleton of one. This is the skeleton of the dead radiolaria. This is something that's called radiolaria art. If you Google, there's tons of people who do radiolaria art. Okay? But they are really good representations of what happens. Think of the skeleton of the subbubble and the skeleton of the radiolarias in the nucleus. I am guessing biologist is associated with the way they move. This is surface tension in the wall. Okay. So, look at the similarities, the radiolarias, the silk. And then these are honeycombs. Okay? And it's not, what's the pattern that I would like you to have discovered by now? I'm looking at these. They all come together, the silk, the skeleton, in trees, groups of trees with angles of 120. There's a good reason that's, imagine that I give you a piece of paper, I put 3 points, and I tell you build the shortest curve joining the 3 points. That's what you do. Okay. So this is your GMT. We will see more about it in a little bit, but okay. Oh, sorry, I got it. This one I wanted you to see, sorry. The pieces, while you're able to see the 3 joining of trees, I want to add a little bit of an illustration of what happens here. What happens here is that you have 4 sheets coming together and they come in. So sometimes things look like that, and so sometimes this is a tetrahedron. I want you to see how the pieces come together. Okay? These are the jointures you see. Okay. Harmonic analysis. What piece of harmonic analysis do I want to talk about? Is harmonic analysis is excellent at decomposing a complicated thing into simpler things. So what complicated thing? I'm looking at a signal. Imagine when you're listening to music, especially if you're in the car. I share my car with my kids, and I know that every time I get into the car, the radio has been changed because, I guess, depending on, they like some wavelengths more than I do. And so basically what happens is that what the sound is superposition of wavelengths. Let's see if this shows well in this light or not. So what happens? Sound, this is sound. Okay, this is what you're hearing. And what happens is that you can decompose it into different waves of different wavelengths, different frequency. And, it's, so what harmonic analysis allows you to do is, I give you the complicated thing, and I give you a procedure to decompose it into simple. Let me give you another example of this decomposition. I give you like this, and I want to decompose it. It's called a Whitney decomposition. What is a Whitney decomposition? Let me show you 2 Whitney decompositions. This one, there's a little bit of color. I want to decompose. I want to fill this shape by squares. And I want the squares to have the following property. The size of the square is proportional to the distance of the square to the boundary. Harmonic analysis is very important, it's very useful, but this is a way in which harmonic analysis decomposes things into simpler things. And although it will not be apparent, this decomposition is something that plays a role in everything that I'm going to say afterwards. I was looking for, when you give a talk, and it's a general talk, and sometimes, you could try to go too deep into your math and forget that lots of mathematics is really motivated by real life. I said, okay, let me find an example. Okay, so this is going to be a very easy slide. I want to say it comes from a medical website, okay, so it's not from a math website, and I wanted to find an application. So it starts, as you say, it has to do with hearing aids, and so this is the math introduction to the medical website, to the medical article, that says that the Fourier analysis was named after Joseph Fourier, who's a French mathematician and physicist, and what they are trying to do is that any repetitive waveform, sound, can be broken into a series of sine waves at appropriate amplitudes and phases. And so making this example is not too different from the one before. I put it there partially because I also was concerned that the previous picture was not going to show. Let's see why they cared about this. So in practice, the software and electronic devices, so this was something about hearing aids, okay, that generate frequency. They use the fast Fourier transform. So the Fourier transform is the thing that allows you to decompose your wave, your sound, into lots of different phases. Of course, when you do an application, if you're doing, you cannot take every single little piece. You only take some, okay? And so that's what the fast Fourier transform, and it's a way to compute some of the most important parts of the sound. And what they say is that this is very, very important because that's what our brain does when we hear sound. And if you're trying to help somebody who needs a hearing aid, that's what your hearing aid needs to do. Okay? So this is an example of where the Fourier transform is an application. I wish the other one that if you have ever been in a recording studio and if you have ever been in front of a very large typewriter, what you see is exactly that. You get to play with the wavelength and then decide what sounds better and what doesn't sound. That's it. Okay? So, what do I want you to take from your very, very biased introduction to harmonic analysis is an area of mathematics that allows you to decompose complicated things into simpler things. We will see how it happens. Okay. And now let's go to the mathematics of your coffee. Okay. What's behind cooling your cup of coffee? Okay, so what do I want you to focus on? Not the coffee, how it smells, right? But what I want you to do, you have a cup. It was at room temperature. You start cooling the coffee. There's a heat source in the middle. Okay? We all know that we drink coffee from the edge, not because it's more elegant, it's because it's cooler at the edge. Correct? If you're put in, it's a maximum principle. Okay, so the Laplacian is the operator that governs the heat conduction for your coffee or for anything, okay, in a homogeneous medium. Here is the picture. So I couldn't find a picture, a disclaimer. I didn't do any of the pictures. I borrowed them. And I try to give credit to where I borrowed them from. I'm not good at drawing pictures. So this is a square cup that was at a given temperature. Your heat source is at the top, and what you're seeing is the heat moving. Okay? That's for the heat distribution. And what do you know from your coffee? If you leave it long enough, it's going to be at room temperature, and most likely not good to drink anymore if you like full coffee. Okay. A harmonic function represents a steady state. What happens once, everything, the heat has distributed. Of course, in your cup of coffee, it becomes constant temperature, but if you have heat from heat sources around, you'll see picture. So, this is the case where, imagine, so, you decide that the temperature of, we look at the harmonic function or the temperature in this annular region is a fixed temperature here, and you're putting these which remain always there. So the darker red it is, the hotter it is, and this is this is the graph of your harmonic function. Okay? I'm interested, remember, like I just spent some time doing harmonic analysis, so I am interested in finding simpler pieces. Simpler pieces are building blocks, like the same way that simple wavelengths help with the sound. I am trying to find what are going to be the building blocks in my case. And so in here, I am interested, one of my building blocks, very important building blocks. Imagine I'm on R3, and I have a heat source here at the origin, infinite heat source, and I'm interested in seeing what happens to the heat. And so this is the picture of the heat, and what you are seeing here is a function that depends radially, is inversely from the distance to the origin. Okay. It's 1 over the distance to the origin. And now I am interested, my building block is rather than imagine that I have this heat source in all of space, I'm going to put it on the disk. Now, sorry, turn it around. I put the heat source at the top, and I want to see if it's 0 on the disk and infinite at the point 0500, what does the picture look like? And it looks like it. So I have something very, very nice, and it goes all the way to infinity. Okay? What you're seeing here is the green function in the unit ball in R. Green function. Green function is a building block. Okay, and associated, I have a Green's function, and so now associated to any bounded domain in Rn, imagine R3 if you want, every time I choose a point x, like I chose that point x over there exists a measure associated at the boundary. Okay, so there's this Green's function, mysterious Green's function I built, you're seeing the picture, and associated to it, there is a measure. I'm going to illustrate, I'm not going to tell you about it. Let me tell you who it is. If you have the normal derivative of the Green's function relates to the harmonic measure, but sometimes that doesn't exist, so let me tell you who this harmonic measure is. So I have Laplace's operator, the operator that governs the heat transmission. Okay? Associated to the Laplacian, I have this Green function, and I have this thing that I call the harmonic measure with pole x. Let me show you this mysterious thing. What is this? So I'm choosing as my domain the sphere. I choose x, the point inside, and the harmonic measure is a measure. So on the sphere is the following thing. It represents the probability that if I start a Brownian motion, so a random walk from x all the way to the boundary, I'm going to hit at some point the boundary, and it's the probability that if I start at x, I will first hit the boundary at a point e. Okay. So many of the things I'm going to say here with respect to PDEs can be formulated in probability terms, but we're not going to do that.
So in this case, the boundary of the sphere wouldn't be 0?
No, the bound is the boundary of the ball. My sphere, my domain is the ball.
Okay.
And my boundary is the sphere.
Oh, okay.
Okay? Like I should have said, when I look at things, and as much as possible, I look at what's inside. So in the Romanesco, perfect example, the Romanesco, I'm not looking only, I know we all focus on the boundary is pretty. I was looking at what was inside and what I want to understand with the boundary. Okay. So, we're back. We have all the tools, and here's the question. We want to distinguish between these two things. Okay, Romanesco on one side, a beautiful mango on the other side. If you were 3 years old, you will tell me it's very easy. It's yaki and yaki, correct? Well, that's not the criteria we're going to use. So, how did I learn it? Actually, I didn't learn this from my own kids. I remember I was at the supermarket, and I see a kid. The kid asked me, is this yummy or yaki? Which I guess is the criteria for. But no, okay. That's actually a value judgment. I don't want to go there. So what I want to do, I know it's silly. I mean, why did I put this pictures rather than mathematical pictures because hopefully these talk to you and these are things that you most likely have held. So I want to say how using the tools that I just put on the board, we're going to try to distinguish. Okay, so geometric measure theory provides a language that describes roughness versus smoothness. Okay, so I will tell you what are the two things we're going to look at. Harmonic analysis, like potential theory, provides the tools to decompose harmonic functions into building blocks. What harmonic functions am I talking about? If you think of it, I'm going to think of both the Romanesco and the Mango as a domain. In fact, I want to throw some mathematical domain, but think of them as a domain, what's inside, okay? I'm going to build the harmonic functions on them, and I'm going to use the building blocks that come from there to try to determine whether the objects that I'm seeing are rough or smooth, according to what GMT told me was rough and smooth. And these building blocks that harmonic analysis tells me how to use are the Green's function and the harmonic measure that I described. Okay? So hopefully now you see I did this introduction. Now this introduction gives me the tools that I need to distinguish between the two. Okay. So, what does geometric measure theory allow me to detect? It allows me to detect the existence of tangents. Okay? Tangents are exactly what you imagine. I will draw some, but you all have taken some classes. You know that a tangent, you have a tangent if the surface or if the graph of function is well approximated by a flat thing of the right dimension. And well means infinitesimally, that if you draw a picture on the computer, on the calculator, and you zoom in, and you zoom in, and you zoom in, then more and more and more like each other. It also tells us a way to see how the length of the surface area behaves. And these will be our criteria for roughness and smoothness. Harmonic analysis allows us to look at the behavior of harmonic functions, okay? And so here is what we do. We can see the doubling properties of the harmonic measure. Sounds silly, but that's an important criteria. And the relationship between the harmonic measure and the length of the surface area of the boundary. Okay. So these are the things that if you want, I'm going to be looking for, and it will let me say if something is nice, is rough, is okay. So, why do I care about this? Okay. Not because I want to distinguish between the Romanesco and the Mango, but because, so from the area of analysis I come from, I was very interested. When you learn partial differential equations in advanced class, it always tells you, if the domain is nice, a nice domain in the ball, the solution is really nice. And we all take that for granted. And I have been very interested in the opposite question. If I know that all the solutions are nice on a given domain, do I know that the domain is nice? To what extent do these two things talk to each other and tell you that they correspond? Okay. So, I asked these in terms of the Green's function and the harmonic measure. And I'm going to, so what do I really want to make it concrete? I want to understand whether the behavior, and I will draw the pictures in a second, of the harmonic function near the boundary of the domain can tell me the difference between a ball, a square, and a snowflake. I'll tell you, I draw a snowflake. And what happens in the case when the interior of the domain is not a homogeneous medium? I think I'm not going to have that much time to talk about that, but okay, here are my domains. Okay, so I'm going to prove 4 domains, and I want to understand if I can really distinguish. A smooth domain, this is what I want to keep you in mind. A Lipschitz domain. What's a Lipschitz domain? It's a domain that locally can be written as the area above a graph of the Lipschitz function. What's a Lipschitz function? Absolute value is your favorite Lipschitz function. It's a function that allows wedges like these, but not worse things. I'm going to look at snowball. What's a snow? So this is a quasi-ball. For those of you who know the definition, this is the quasi-conformal image of a ball by a global quasi-conformal transformation. But if you have never seen the definition, I guess that you have seen something like this. What is this? This is a fractal that you produce by iteration. Okay? And then there's this one. So bear with me for a second. What is this? This is the complement of the four-corner Cantor set. So what's the four-corner Cantor set? You start with the unit square. You divide it into 16 little squares. You keep the 4 at the edge. These 4. You do the same thing. You do the same thing. And what you have at the end is a white page, except those little dots. And what I want to understand is, can I distinguish between, using the tools I described, between these 4 domains?
Sorry, Tatiana, the last domain is the complement of that, what
It
is
is-
right? Or
yes.
it's the set that is right?
No, it's the complement, is what's left of my page minus all those little dots. Okay? There's lots of little dots, but you cannot see. Okay? Okay. So, these, from now on, I'm going to be talking about these domains. Can we distinguish? Okay. So, existence of tangents. Remember, I said GMT tells me I'm going to look at 2 things. Out of the GMT box, I look at the existence of tangents and at the length. Existence of tangents. For which ones of these guys do I have tangents? If not at every point, at almost every point. Okay, I don't care about 2 or 3 little corners.
Smooth ellipses.
Smooth ellipses, exactly that side. Okay, here we go. They look the same from this point of view. Okay. Now let's go to length. So if I look at the length, and I'm only allowed to walk on an ant, and I'm only allowed to walk around the domain. So the distance between here and here is the same. It's comparable, it's finite, comparable to Euclidean distance. And same thing here. These corners just add a little bit, but we all go around corners all the time, so it's fine. With the length, what do you think happens with the other 2? Sorry? So the length in the snowball, you are correct. In the snowball, if I go from one to the other, I theoretically can go. I see the line, therefore I can go, but it's correct. The length is infinite between the 2. And what happens on the other one?
It's connected.
It's totally disconnected. So the question I ask is completely stupid. How can I go from one point to the other? Fine. I agree. I cannot go. But I can measure the length. You all have seen the Cantor set of the line, and you can, and maybe you have even more 5 Cantor sets, and you can measure the length. So, and that again is about the equivalent of the length, which is a Hausdorff distance. So it turns out, well, here is what we just said, but the boundary of the complement of the 4-cornered Cantor set has finite length. And length should be heard as Hausdorff distance. In fact, it's really better. So if I'm looking at whether distances on these sets are finite or not, unfortunately, it looks like the smooth and the Cantor set. Remember, remove all your preconceived ideas, what they look like. If I only gave you length and define length in a way that corresponds to these, theoretically you see the same. Okay, so you might be thinking this is not very good. Or you think it is very good. So, from the Hausdorff dimension, which is a very important notion of the geometric measure theory, which I not defined, these 3 things look the same. Okay, but clearly I have to refine because I don't know about you, but to me these look very different. If I had gone further into geometric measure theory, they're really different. This is almost the opposite of the other ones, but of course. Okay. Now, what happens for the quasi-ball is exactly what you said. This distance is infinite. And if you imagine what happens to the pure microscopic ends, it has to go to every single little one of these peaks, and inside each peak there's another peak, and the pure end will never get there. Okay? Actually, it will never get anywhere. That's for the philosophy talk, not for the Okay, so let me see. I'm going to say something. I'm not going to get to the end of my talk. I wanted to get to one particular spot, and then you're going to close your eyes for 3 seconds until I get to the end, okay? So that it doesn't look like I went through lots of things that I need to talk about. Okay, so now I want to look at the similarities of the harmonic analysis. So every harmonic function on these domains is built using the harmonic measure. Okay, so that's why I call it the building block. In fact, every harmonic function is something that satisfies the differential operator. If you don't know what that means, please ignore it for a minute. That's what it means. But every harmonic function with boundary values f can be written as an integral. And this thing over here is that harmonic measure that I talked about. So that's why when I talk about harmonic measures, I only focus on the building block. But, so I can look at the harmonic measures with 4 domains, and it turns out that all those 4 domains, the following things hold. If you have 2 points, then the 2 harmonic measures are equivalent, which means basically they see, no matter whether you start in X or you start in Y, you see the boundary more or less the same. And the harmonic measure is doubling. Remember I said we were going to talk about doubling? The doubling properties. What does it mean that it's doubling? It means that if I take that the measure of the wall of radius 2r is controlled by the measure of the wall of radius r. This is telling you that things are not going haywire. It's also telling you that there's no atoms and there's no points that are, where the measure is concentrated. I wanted to highlight these because historically, this property has played a very important role, all in harmonic analysis, but in particular in history. Okay, so what happens? What happens is the following. We look at, through the brief history, we look at these domains and where these domains fall, and we see that we have always proven, under some lights, they all have the same property. So this is the number of people that have made contributions. Let me not dwell on that. But what we want to know is, okay, they have similar properties. They're doubling, but can they distinguish? Is there something in the harmonic measure that allows me to distinguish? And in particular, I don't know about you, but the one I'm really bothered about is the fact that at some point in GMT, I put the smooth domain, the lectures domain, and the complement of the 4-corner Cantor set in the same bag. And that doesn't seem right. Okay? You're seeing all my prejudices come out. I don't want to put the full 4-corner Cantor set with the circle, but I want to be able to distinguish them. Okay? And so that's one of the motivations. And so here is what happened. In 1977, Dalton proved that you have the length and the harmonic measure, and they're mutually absolutely continuous. Okay? That means if one has measure 0, the other one has measure 0, and there's a little bit more. And the question is, does the same thing happen for the 4-corner Cantor set? Okay? Are there other domains? So now what I'm giving you is a list of questions that has motivated actually the research that we're doing now, including the fact that questions that I asked, is there a way to distinguish between the circle and the 4-corner Cantor set? Not by the harmonic measure necessarily, but by a cousin of it. Is the question that has motivated the research that we put out this week, okay? And it's that we're very happy. I will show you some pictures. Okay. Are there other classes or domains where the result is true? And what does the fact that this property holds tells us about the geometry of the domain? Okay, so now I have focused everything in terms of the harmonic measure. Does a harmonic measure determine the geometry of the domain? If I tell you I have a harmonic measure that's doubling, can you tell me something about the geometry of the domain? I now will answer that. If I have a harmonic measure that's an infinity weight, which means it's mutually absolutely continuous but in a quantitative way, what does that mean? It means if this is small enough, then this is small enough. Can I tell you something about the geometry of the domain? That's something we're going to see in a second. Okay. And I'm about to... Okay, so to be able to answer that question, I should talk for a second about these domains that are called NTA. So what's an NTA domain? It's a non-tangentially accessible domain. It means that you can draw balls inside and outside. And it means that every time, let me draw here, you are inside the domain and you put 2 points, you can join these 2 points by a necklace. That looks like this. And I'm going to not give you the definition of these. I'm going to say that looks like this. Okay? Okay. And we look at domains for which the surface measure of the ball is like R to the n minus 1. Think of it, the surface of the boundary has a Euclidean volume. Okay. And to answer the question that I asked, what happens is the following. David and Jerris, in a sense, prove that if you have an NTA domain and the boundary is outwards regular, then omega is infinite. That's the magic property that I put there. And then they also show that the domain is uniformly rectifiable, which means each ball can be described as 90% one Lipschitz graph and another piece. Jump over these because it is completed. So what we prove using that is under minimum hypothesis of the domain, the following things are equivalent. The domain is NTA without first regular boundary. The domain is uniformly rectifiable. And omega is A infinity. What does this mean? It means that this A infinity property does describe the geometry of the boundary or the geometry of the domain, however you would like to look at it. Okay? And so why is that important? Well, this is the effort of a team, and these are their names. And so why is that important? Because all of the domains that I pictured satisfy the minimum hypothesis. Okay? So, but the complement of the 4-corner Cantor set has outwards regular boundary. On the other hand, it's not NTA. NTA requires that you have a ball in the exterior. The complement of the 4-corner Cantor set doesn't have an exterior. The exterior is the interior of the complement. There's nothing. Okay, so the interior of the complement. So harmonic measure is telling us, yes, look, I can tell you the difference between the 2 of them. And so here is my summary. From very macroscopically, whether you have interior and exterior balls and these pearls, which are called Harnack chains, they're all the same. From the behavior of the surface measure, these 3 look the same. And from the point of view of the harmonic measure, these 2 are the same, the smooth and the Lipschitz. And for me, I'm happy now. I am in geometric measure theory. For me, my definition of smooth is Lipschitz. Therefore, I don't see corners. This is perfect. Okay? So that's, hopefully I have managed to convince you that under 3 lenses, we can distinguish some things. There's many questions that remain. Unfortunately, I'm not going to be able to describe them. I'll be very glad if you have questions further to answer. I just need you to close your eyes for 3 seconds while I get to the last slide I want to show, because I don't want, it's horrible when you have these speakers that underestimated or overestimated, it depends which one there is, the time. And now it's going to rush through a number of things that maybe you will have to see, or you're glad you didn't see. But I want to show you something I know. That I want you to close your eyes so you don't see over 1 inch. Okay? Okay, come on. Close your eyes. And you can open your eyes. Okay, so what's this? Now, this is a team effort. Math is a team effort. Okay? And what you are seeing here is my team. These are the people that have contributed to either the work that I am describing now or the work I'm currently doing. I also want to illustrate by these that people, there's lots of different ages represented in here, and there is an array of people. We all contribute. You are seeing my postdocs, my graduate students, and my mentors right there. Okay. So, thank you very much.